Hi student, today I am going to demonstrate a case study that I developed on the ARCH model, autoregressive conditional heteroscedastic model in R, and I will take a real life data, and first things that I will show you how to identify the appropriate model based on AIC, ACF and PACF functions from, and the final selection definitely would be based on the AIC, and after selection that will feed the ARMA or ARIMA model, and then from there the residual will be extracted, and based on the residual we will see whether any evidence of volatility exists in the data or not. If exists, then we will try to fit appropriate ARCH model, and there also we will try to explore the order of ARCH model by graphically ACF and PACF functions, and finally the AIC based selection criteria would be used to select the appropriate ARCH model. So let's focus on the data. The data that I took is the BEAST 100 index USD based from year 1988 to 2013, taken from the web, and here mainly the interest of the data. I just displayed a header of the data. So this is the variable of my interest that I use to demonstrate the ARCH model analysis. So these two variables are of our interest, and the whole data was entered in a Excel sheet, and that Excel file name was nxu100.csv. So first thing that we have to do, as you know, that need to be import in R console. The CSV is most easiest way to import the data. So if you just import the data and store in a object called data, then you can easily access all the columns that are there, but our main interest is the USD based BEAST 100 index. So before we go to the analysis, we really need to explore through the exploratory analysis about the possible choice of the models. So here first things that I will do here, I'll ACF plot that can be done by ACF function, which is available in R. So and I used a log of the index, log return. So the maximum log lag.max I set to 150, and that will give you the plot looks like this. If you just observe the autocorrelation over the lags, you will see it's gradually decreasing, but actually it is not diminishing. So when you get this kind of ACF plots, then that indicates you that you better can take the difference of lag. Differencing is very much needed here to tackle this kind of data. So as I mentioned, the ACF is slowly decreasing, but it's not drying down. So we can do the one lag difference. So that to get this, there is a function called diff. So just the log USD based, that log variable can be passed through diff within the same function ACF, and I said the lag maximum is 1.5, and then the ACF plot would look like this. If you see, just I took one lag difference, that itself reduced the autocorrelation values. It is, if you see here only is here, that it is actually lag 1 showing significant, others are there but they are not beyond the confidence limit. So the significant lines, so only lag 1 is appropriate for this difference, that is the moving average order. And then I will look for the AR component, and there I use the partial autocorrelation function. That partial autocorrelation function can be drawn by a PACF function, where the same way you can include the variable, log variable, and maximum lag I set to 15, and then you will get a plot something like this, where if you observe, that it seems that log 1 and I mean two lags are actually exceeding the insignificant line. So possibly 1 or 2 lags might be appropriate for air structure. So I mean till 2 lags, and then PSCF cuts off. So as I mentioned. So next we will also explore the PSCF for the differencing data. So it's just 1 lag difference that was taken, and same way the way we did for ACF, just diff function can be used, and the log series can be passed through diff function, and lag max was set to 15, and then you will see the plots something like this. You will see here, I mean lag 2 is showing, I mean others are going here and there, but significantly we can see the lag 2 might be the quite possible choice for air structure. So then we'll move to, I mean considering a model called ARIMA. So we'll take the ARIMA model selection. So as a whole, if you see that model selection, all it's together, I mean just combine all the plots together, then you can easily guess that there is a moving average component, there is a air component, and there is a differencing component. So it is actually autoregressive integrated moving average model. So that the order of the model can be confirmed by AIC. So we will first try, I mean different choices of ARIMA orders. We will calculate the AIC, and then we will compare the AIC and choose the appropriate order for ARIMA. So the ARIMA is a function that can be used. So log variable would be passed through ARIMA, and order can be mentioned as I start with 0, 1, 0 and $AIC. So the whole thing, if I use dollar, then that will give you the AIC values. Similarly, if we change the order from 0, 1, 0 to 1, 1, 0, then 0, 1, 1, then 1, 1, 1, then 0, 1, 2, then 2, 1, 0, 2, 1, 1 and 2, 1, 2. And if I just summarize all, it looks like the most smallest, I mean the least AIC that was observed for 2, 1, 2. So we can select the ARIMA order as 2, 1, 2 based on the AIC, that is the lowest AIC. So now we will feed the ARIMA 2, 1, 2. As I told, ARIMA is the function. So I fitted the ARIMA model same way that was done for calculating the AIC. So ARIMA log data $USD dot based, and order is equals to 2, 1 and 2. That is named as ARIMA 1, 2 I stored, and if you just want to display, just type ARIMA 2, 1, 2. That will give you the results of ARIMA, that is 2 air component and 2 moving average component, and that sigma square also is given. And finally the model that we will get from this fitting is yt minus 1 equals to minus 0.95 into yt minus 1 minus yt minus 2 minus 0.192 into yt minus 2 minus yt minus 3 plus 0.660, that is the moving average coefficient epsilon t minus 1 plus second moving average coefficient was 0.263, so 0.264 epsilon t minus 2 plus epsilon t. So that is the ARIMA model that was fitted. So next objective is to extract the residual from it, because there we will see the evidence of volatility. So let's look for the evidence of volatility in the residual series. To get the residual, we can that ARIMA object, ARIMA 212 object that I created. So ARIMA object $race, if I write, that will provide you the residual of that particular model. So that residual was stored in race.arima 212, and then finally the square residual was derived by just squaring the residual series, and we just plotted the residual. If we plot the residual, just square dot race dot residual, then square residual is passed through the plot function, and that will give you the plots looks like this. If you see the plots, then clearly you can find several clusters there. The square residual plot shows some clusters of volatility at some points of time. Especially here, these are the three locations are quite prominent clusters. That cluster indicating the heteroscedasticity in the variance. So variance is not constant. Of the residual variance is not constant. That is a strong evidence of the volatility. So we should take care of the volatility by the alternative models. So here I feed the arch model to address this volatility here. So ACF and PACF of the square residual will help out to identify the order of arc model. So for that, here I wanted to plot both ACF and PACF together in a plot. So for that, I use the function called pair, where MF row equals to C1, 2. That means it would be one row but two columns, and two plots. One plot would be the left panel, another plot would be the right panel. And this way, this particular function will create this ACF and PACF function of the square residuals. And again, I set to 1 structure of the plot. So that is MF row, pair MF row C equals to 1, 1, and this is the ACF and PACF of the square residuals. And then if just use the function called use the package that in R is a TSA. The TSA function will be used here to fit the arch model. So first things that we have to do, we have to choose the appropriate order for the arch model based on the AIC, because from the plots it was not clear what would be the exact, is giving some instruction, but it's not clear what would be the exact order of the arch model. So that can be done only through AIC. So for that, we can calculate the AIC. I just developed a very simple function here, my AIC, where if you see this function, the feet Q and D can be provided, and that function will calculate the AIC. And then and for the 0 order, for 0 order, that function cannot provide the AIC. So for that, I calculated separately for AIC 0 by the above formula, and then I use the my AIC function all the time to generate the AIC for other orders. So for 01, 02, 03, 04, then up to 010 that I explored for AIC. Sorry, 010, 11, and then the arch 10 was found to be most significant, appropriate. The arch 10 data was, if you see the previous one, where the arch 10 is showing minus 57,055.59, which is the lowest among all that was explored. So 10 was considered to be the choice of arch order, and to generate the arch output, I use the function GARCH, GARCH, that is available in TSA package, that just pass the residual of ARIMA 212 and then order 0 to 0, 10. So first the 0 for the gauge component, but here I said the gauge component 0 and arch component is 10, and trace equals to false means I don't want to see the intermittent steps that normally it shows. That will directly show you the summary instead of the step by step iterations. The summary can be generated just by summary function of the same arch object, and that will generate the arch 10 order 10 model, and that you will see here the coefficients from 11 coefficients including the A naught, and here is the p value, and also there is some diagnostics test that also available, that is Jarker-Bear test, and that all are this is also significant, and L-Young test of the square residuals is indicating it is not significant. That means there is no further evidence of autocorrelations in the residuals, so that has been taken care by this arch model. So that's all about the arch model. From this model that we have seen how to select the appropriate order for a ARIMA model, and then from there how to extract the residual from this model, and finally to see the evidence of volatility, and if it exists how to identify the appropriate arch model for that particular to address that volatility. And here by the particular package called TSA that we used, and the GARCH is the function that we used where we mention the order as 0 and 0 and p. So that indicates it's the arch model. I hopefully after completion of this module you would be able to understand how the arch model need to be analyzed in R.